All right, I kind of want to get rolling with the content because I have what I hope is a bunch of cool stuff today. I hope you really like it. Before we get started with the actual content, though, just a couple of things. So this one is pretty random. A while back when we were doing the Python stuff, I said that it's cool if you want to see the attributes of an object to use the dict method. So double underscore dict, double underscore, and that will, in many cases, will show you the attributes of the object. And you can use that to, remember the name of something that you forgot or figure out what methods are available and so on. But that advice is kind of incomplete. I should have said more about that. So the dict method doesn't always work. And in fact, it probably isn't the thing you should try first because that's what dir is for. So if you call dir, which is a function on any Python object, it will tell you the things that you can put after a dot after that object name. So if you want to do numpy dot whatever and see what the possible whatevers are, you can call dir on the numpy module object and it will return this extremely long list. I had to put an ellipsis here to fit it on the screen. There's a ton of NumPy stuff, but that can be kind of a helpful way for you to see like, okay, how many NumPy things are there really? Let me look at them and kind of, see if there's something that looks interesting or applicable to this particular situation. That can be an alternative to Googling. It's maybe more helpful when the object only has a few attributes and you forgot one of the names or whatever. But I find this indispensable. I use this all the time. In some cases, you do have to use dict instead because sometimes a library author has overridden the behavior of the dir function in such a way that it's not actually giving you all the attributes and it's less helpful for what you're trying to do at the moment. So you do kind of need both of those ideas if you want to have a comprehensive way of accessing all of your object's attributes. Nevertheless, I probably should have said to use dir first instead of the double underscore dict double underscore attribute. Let's continue talking about probability now. So far we've developed ideas about probability spaces, random variables, distributions of those random variables, joint distributions when we have multiple random variables. And these topics are kind of what we needed to put in place to start talking about conditional probability. They're useful in their own right, but they're also prerequisites for the next idea that I want to get into. Before we talk about conditional probability, though, I want to warm up with some review from last time, and I'll start out with a question. So what's the difference between knowing the joint distribution of two random variables, x and y, and that's missing here, it should be a y, and knowing the marginal distribution of x and the marginal distribution of y? So this is kind of funny because everyone said the same thing. Even so, there's a couple more that came in after I summarized, and those folks are also saying the same thing. So there's an asymmetry between joint and marginal distributions in that if you have marginal distributions of the two random variables, that's not enough to know how they're related to one another. And if you have the joint distribution, that is enough to know how each one by itself is distributed. So that's not quite what I was going for, but that is what everyone said. So I guess that's the correct answer. So here's the answer I prepared. The joint distribution tells us where the XY pair lies in the plane. Like what are the possible outcomes for what X is and what Y is together and how likely is each one. And it's not just telling us where those probability masses end up if we just consider one of the random variables at a time. So this is the picture that I shared with you last time. The original idea, so this slider controls the animation for the basic idea of a joint distribution. So we have two coin flips and each coin is fair. So each of these four outcomes is equally likely. And we're considering along the x-axis, we're considering the number of heads, and along the y-axis, we're considering the number of tails. It's like this has two heads and no tails, so it goes here. Same for all the others, they go where they go. And we end up with a quarter mass here, a quarter mass there, and a half mass in the middle. So this is the joint distribution of x and y. And if we want the marginal distribution of x, for example, what we can do is project everything down to the x-axis. And there we have a quarter here, a half here. That's the distribution for the x random variable. And there's not a slider for it, but if you did the same thing horizontally to project to the vertical axis, that would give you the marginal distribution for the y random variable. I want to say just briefly why that's the case. because I think I didn't elaborate that last time and it's worth reflecting on. So we have these masses, a quarter here, a half here, and a quarter here. And if we want to know something like, what's the probability that the number of heads is in, let's say, the interval from 1/2 to 3/2, then that corresponds to this big vertical strip. We're asking how much total mass is in this strip. And we can either do that by totaling up the amount of mass in the strip directly, which is just going to give us this mass, or we can do that by taking that mass and pulling it down to the x-axis and then counting it there in this interval here between 1/2 and 3/2. So that's the idea. You can either count it there after you've pulled it down, or count it where it is in that strip. So that's why we're projecting onto the x-axis. There's nothing really special about projecting. It's just a way of kind of doing the mass accounting here. Okay, so here's another question kind of building on this idea and leading into the conditional probability discussion that we're headed towards. So suppose that x is the number of heads in 2 fair coin flips, and y is the number of tails in 2 other fair coin flips. So now we're flipping 4 coins. We're reading x off the first 2 and y off the last 2. So now in this situation, what does the joint distribution of x and y look like, assuming that the correct probability measure is the one that assigns probability mass 1/16 to each of the 16 outcomes for the 4 coin flip experiment? And that's maybe a little hard to describe in words. So if you want a simpler question to answer, just state how many points are in the support of this probability measure. In other words, how many possible values can x comma y take on in the plane? Okay, so a few answers here. I want to hear from someone. So Radhika, do you want to talk about what your answer is here and maybe elaborate on it as much as you want? Right. So let's take a look at a visualization of this. So here's the correct probability distribution for x comma y in this situation. And really what's happening is that there are certain outcomes that are more likely than others. Like having both x and y be 1 is the most likely outcome. And these outcomes sort of on the sides are somewhat less likely, and the ones in the corners are less likely than that. And if you want to see how the marginal distribution emerges from this joint distribution, and this is a little bit different than the other situation where we weren't adding any masses, here when we collapse things down vertically, the masses will add up. So we recover this quarter, half, quarter for the marginal distribution of x. And likewise, and here we do have a slider in this direction, we recover a quarter, half, quarter here as well for this marginal distribution. And then altogether, the joint distribution looks like this. And you would get this just by sort of working out how many ways there are to get each of these things. So like x equals 1, y equals 1. Turns out there are 4 ways to do that. And so we get 4/16, which reduces to a fourth. So these two mathlets together, I really want you to sort of hold them in your head as kind of polar opposites for how joint distributions can look. So in this situation, the two random variables have nothing to do with one another since they pertain to separate coin flips. We'll say that they're independent. We'll talk about that idea in a little bit. But for now, just notice that the masses are sort of more spread out somehow. And we get a marginal distribution by having to sort of add up the masses as we project down to the axis. And in this other situation, the masses are concentrated along a line. So these are very related random variables. If you know one, you know the other. So this is kind of, in some sense, opposite ends of the spectrum for how random variables can be related. And it's also telling you how a joint distribution, the picture of it, can indicate in your mind what those differences are. So if you can see a joint distribution plot, then you can really get a sense for what you're dealing with respect to how the random variables relate to one another. Okay, so let's focus in a little bit. We'll take a little bit of a step back and we'll get back to some of these ideas that we've started developing here. First, what I want to do is focus on this idea of how random variables relate to one another. So this is a really important concept. it's in some sense the foundation of statistics. Almost everything, as we discussed last time, that you want to do in statistics boils down to understanding some sort of relationship between random variables, and conditional probability is one of the key tools for thinking about what those relationships look like. So let's start sort of at the very beginning and just think about what conditional probability is and how we're going to model it. So we have this probability model that we've developed that's supposed to say something about a random experiment, and we have to work these real world ideas into the model so that we can translate all of our questions back and forth across that barrier. And the idea that we're going to be trying to develop a translation for here is the idea of partial information. So we discover something about the outcome of our experiment before we know the outcome exactly. So once we know the outcome exactly, we don't need probability anymore. We know exactly what happened. But if we only know partially what happened, there's still probability to do. There's some randomness outstanding, if you will. So for example, if we flip a fair coin twice, then we will see the result. If in the sort of normal course of things, if you physically flip a fair coin twice, you will see the result of the first flip because you have to record it before you flip it again and record that result. So in that in-between state, you have partial information on what the outcome of your two-flip experiment is going to be. And in many cases, it's useful to define a new probability measure which updates the original probability measure we had to reflect this intermediate knowledge we have about the outcome of the experiment. And this is called a conditional probability measure. So I want to try to develop this idea in a very bare hands sort of way so that when we have formulas coming out, they're grounded in something. So let's go with the two-coin flip experiment for an example. And imagine that the first flip turned out to be a tail. So that's telling us that the little omegas, the set of things that could have happened that are incompatible with that observation, they should get a new probability of 0, an updated probability of 0, because we can exclude those from consideration. And that makes sense, but it's not enough to just take some of the elements of a sample space and squash their probability to 0, because now we'll have a total amount of probability mass less than 1, and that's no good. So we have to boost all of the other probabilities to compensate. And it makes sense to do this in a way that preserves their proportion. So if something was twice as likely as something else before, and they're both still possible, then it should be twice as likely after, because we haven't learned anything about the remaining omegas if all we know is that the outcome falls in some particular subset of the sample space. So in the case that the event E is first flip is a tail, then we can rule out these two flips on the bottom, or sorry, these two outcomes on the bottom, these two flip pairs, because they involve the first one being ahead. So those should go down to 0, and the others are going to have to get a boost to compensate. So these are the only two remaining possible elements of the sample space, and they were equally likely originally, so they're equally likely now. Therefore, they're each probability a half. So these are each a half after we make that first observation and update our probability measure. And really, that's it. That's the full sort of concession that we have to make to bridge this gap between the real world concept of partial information, specifically in the form of discovering that the outcome of the experiment falls in some particular set, and the probability model side, how do we actually update our measure? This is all we need. So we're going to get all the formulas for conditional probability that you've seen before in other courses, all from this original observation. So the idea is, if we want a condition on an event, we set the masses in the complement of that event to 0. And then what we have to do is multiply the amount of mass at each remaining point by 1 over the probability of that set. So 1 over the total amount of mass remaining. That way, the total amount of mass remaining after we gross up the probability masses will be 1. So let's write that down as a definition. This is just directly from the data gymnasia content. So if we learn that the little omega selected by Lady Luck from big omega, if we learn that it falls in some set E, then we can update our probability measure on omega to this new one, which we'll call M of omega, and then we'll put a vertical bar here and then E. So this is just notation. There's nothing for you to understand here. Just learn what it means when people write this sort of thing down. What it means is the new probability mass function associated with the partial information that the outcome that actually occurred fell in the set capital E. So that's what all of this is. It's just a function of little omega. And what is it? Well, if little omega does not fall in E, we zero it out. If it does fall in E, then we divide it by probability of E. That's going to increase it, boost it up, so that when we total all of these probability masses up over the whole sample space, we get 1 still. And it's helpful, and probably you've seen this formula many more times than the one that's on the screen now. It's helpful to sort of lift this up from the probability mass function to the probability measure. So instead of little m, we can write capital P. And instead of little omega that we're evaluating the mass at, we're going to evaluate the mass over a whole set. And since we already are using the letter E for the event that we're conditioning on, we're going to use the letter F for that. So the probability of F given E is, well, we should just total up this formula. We should add up all of these probability masses and say what we get. So we get a probability of E in the denominator carrying over from this probability mass function. And then it sort of seems like we would get probability of F in the numerator, except that if there are any little omegas that are not in E, they contribute nothing. So we have to eliminate those. So that's why we intersect with E right here. So this is a formula you've undoubtedly seen before. A probability of F given E is a probability of both events occurring divided by the probability of the event that we're conditioning on. But because we've developed it here from this more basic idea, you can see where it comes from and reason about how it plays out in a given situation without treating it as an axiomatic formula that things are built on top of. You can see here, for example, how if probability E is 0, this formula gives us some problems. And if you back up a little bit, you can see that in this picture, we're assuming that we're conditioning on an event of positive probability in order for any of this to make sense. So if you do want to condition on a probability 0 event, you understand you have to take a different approach than what we did here. Okay, so why are conditional probabilities important? There are lots of ways to think about that. And in some sense, it's maybe too basic of a question, but the many answers that you can give to that question each shed some light on the usefulness of thinking in terms of conditional probabilities. And here's one that's really important, in my opinion. It's often the case that in a given problem, what you have access to from first principles or from some sort of empirical analysis is not actually a value of the probability mass function. It is a conditional probability that shows up along the way. And then you work out the probability mass function based on that. So I'll give you a really simple example. Imagine that we roll a die, and if it shows 2, then we select earn A, or 2 or 1, then we select earn A. And if it shows up anything else, we'll select earn B. And these earns have different numbers of balls in them. Earn A has 1 red ball and 1 blue ball, and earn B has 1 red ball and 3 blue balls. And after we select an earn based on the die roll, we then choose a marble, or sorry, what I call them balls. We choose a ball out of the urn and then record its color. So we could end up, as the final result of this experiment, we could get a red ball from urn A, a blue ball from urn A. You get the idea, red from B, blue from B. Those are the possible outcomes. And there's a value here that's showing up sort of clearly, which is in this question statement, which is 3/4, that's earn B. So the probability of selecting a blue ball from earn B is 3/4. There's 3 blue and 1 red. So that's where 3/4 is coming up. But as we're going to see, 3/4 is not a value of the probability mass function for this setup. It emerges as a conditional probability. So actually, the tables are sort of turned here, where instead of having the probability mass function given to us from the outset, what we actually have are conditional probabilities, and we have to work out the probability mass function. So let's see what that looks like. So the 4 possible outcomes, as we said, are A red, A blue, B red, B blue. And so those are going to be our 4 elements of our sample space. And if we want to work out the probability of any one of these, like let's say A comma blue, then we can say that that's equal to the probability that urn A is selected times the conditional probability of selecting a blue ball given that urn A was selected. So that comes directly from the conditional probability formula that we derived a minute ago. We're just turning it around and putting probability of E over on this left-hand side. And it sort of seems like we're maybe begging the question here because we're using this conditional probability formula, but doesn't the conditional probability itself depend on having the probability measure? And what's really going on is that we're choosing to interpret the information that urn A contains an equal number of blue and red balls as a statement that this conditional probability should be 1/2. So actually the primitive information is this conditional probability, and we work backwards from there to get all of the probability measures. So ultimately we're going to assign a probability of 1/6 coming from 1/2 for the probability of selecting a blue ball times 1/3 for the probability of selecting urn A. So at the end of the day, the actual probability mass function that assigns probability masses to actual outcomes for the experiment is going to have a value of 1/6 for this particular outcome, A comma blue. And if you work out the other three, similarly, just multiplying through this tree, the probabilities that get assigned to the other three outcomes are 1/6, 1/6, and 1/2. So we have 3 probability 1/6 events and 1 probability 1/2 event. And then if we wanted to sort of check that everything is consistent, we could go back and work out that the probability of E and F divided by the probability of, should be E here. I think there's a typo. Oh no, I think it just switched around. I switched around E and F, so that's kind of confusing. Maybe I'll go back and fix this later. I suddenly switched E and F, so the E and F in this message are different from the original one. But anyway, we can derive the probability of selecting a blue ball from urn B, given that urn B was selected. It's sort of obvious in the picture it's 3/4, but we can also work it out from the overall probability measure and see that it's 1/2 divided by 2/3, which is 3/4. So that checks out. And the point of sort of doing this both ways is to emphasize that a probability space can be specified either by a tree diagram showing conditional probabilities at each branch, or by the probability space, which in the picture is the set of endpoints of the tree diagram. And we can translate back and forth between these two representations by multiplying along branches to get from the conditional probabilities to the actual probability mass function, or dividing to go back the other way, dividing probability mass function values to get conditional probabilities that go in the branches of the tree diagram. So yeah, there should have been a question there, honestly, oversight in my script preparation, but I'll ask you 4 questions. So here's one. Where did the 1/3 come from for the event A comma blue? So we're talking about right here, when we worked out the probability event A comma blue, I had 1/2 times 1/3 right here. So the 1/3 comes from the probability of selecting urn A. So urn A requires that we roll a 1 or a 2, and there are 6 outcomes for the die. Each is supposed to be equally likely. So that means there's a 2 in 6, or in other words, 1/3 chance that we selected urn A. And then a 1/2 chance we selected blue. So we have 1/3 times 1/2 is 1/6. Yeah, so just to maybe put a picture, so I'll answer this question from Hardy. So the probability masses in the original diagram would lie on the branches. Yes, so just to maybe make a figure to clarify this point. So I'll draw the branching diagram here, and then we'll put conditional probabilities in, let's say, blue. So this is 1/3, 1/2, 1/2, 2/3, 3/4, 1/4. So these are all conditional probabilities. But the actual probability masses, and let's switch color, maybe to orange. So the actual probability masses lie here. So these are your M of omegas. So these are your actual omegas. There are 4 of them. And the probability masses are here. So we multiply. So this is 1/6, 1/6, and 1/2. So and these are the M's. So this is the actual probability masses. And what lives on the branches of the diagram are conditional probabilities. And so we can go back and forth between those two using either multiplying along branches to go left to right, or by dividing, totaling and dividing to go right to left. All right, so let's move forward into discussion of independence. So the next step from conditional probability is going to be to talk about independence. So in the context of a random experiment, we say that two events, E and F, are independent if knowledge of the occurrence of one of the events doesn't give any information about the occurrence of the other event. So in other words, once we have the language of conditional probability, we can say the conditional probability of E given F is just the same as the probability of E. So knowing that F occurred doesn't tell us anything different about the probability that E will occur. In other words, updating our probability measure with the knowledge that the outcome falls in the set F doesn't tell us anything about E, and vice versa. So we can write equations for this. We can say probability E equals probability of E and F divided by probability of F. So this is just a statement that probability of E equals a conditional probability of E given F. Same idea over here. And handily, both of these equations rearrange to the same thing. So if we are assuming, as we must in order to make sense of these formulas in the first place, that probability E and probability of F are non-zero, we can just move the denominator over and we get exactly the same equation. And it's also kind of nice because if we focus on this equation, we don't have denominators at all. So we can eliminate the caveat that the two events have to have positive probability. So we take that as the definition. So we have a probability space and two events defined on that same probability space, then the probability of E and F is equal to the product of the probability of E and the probability of F. So if that is true, we say the events are independent. And if the events are independent, that equation must be true. So this is a definition. So if we want to check whether two positive probability events are independent, we really probably just want to use this equation. We could use either of the other two since they contain the same information. And in some cases that's helpful, but often it'll be easier just to say, okay, for these two events, if they both occur, what's the probability of that? If one or the other occurs, let's see what the probability of each of those are. And we'll just check this equation. Does the product of those two things equal the other thing? So let's look at a concrete example. So suppose that A, so we'll have a six-sided die and we'll just roll it. And suppose that A is the event that we get an even number, B is the event that we get an odd number, and C is the event that the outcome of the roll is less than or equal to 4. So how can we tell, let's take these one at a time. I'll throw a question in here. How can tell that A and B are not independent? Okay, good. So we had some good answers that came in here. So let's see how it works out with the equation. So conceptually, if one occurs, the other can't occur. So that means that their probability, the probability of their both occurring is 0, yet each one has positive probability. So the product of their probabilities is positive. Specifically, it's 1/4, but it doesn't matter if it's positive and they can't occur jointly, then they can't be independent. So in fact, when we talk about positive probability events, earlier we said mutual exclusivity is a different concept than independence. In fact, they're non-overlapping. You can't have mutually exclusive events, which are also independent if we're focused on positive probability events. There's a question, by the way, about positive probability events I want to answer. So does positive probability mean non-zero? Yes. Positive probability means that the probability is in the interval from 0 to 1, excluding 0. Yeah, so positive probability events are just events that have a positive probability of happening. So if I flip 2 coins and I count the total number of heads, the probability that that number is 6 is 0. That is a thing that can't happen. It has probability 0. Whereas the probability that I get 2 heads and 2 flips is 1/4. It's positive. So positive probability just means something that when the experiment is run, it can happen. It has a positive probability of happening. You will watch YouTube videos sometimes where people will use the word can in this context a little bit differently than I do. They'll say, for example, that if you choose a random number between 0 and 1 uniformly, so a continuous random number between 0 and 1, there's a zero probability that the number that you choose is exactly a half, but some people will say, well, it can happen because it's in the interval. I would not say that. I say that if something has a probability 0, then you know with an absolute certainty that it will not occur. And so it's weird to say that it can occur. It's just an abuse of the term can. So anyway, positive probability means it has a positive amount of probability mass associated with it. Okay, what about A and C? So are A and C independent? All right, we're split on this one. Let me share the answers. Folks are trying to make up their mind. So there's tension here between the interpretation of independence where we think, well, if you're drawing from the same source of randomness, in this case, a die roll, you can't be independent, right? If you're looking at the same thing, you need to look at fresh things. Get your own die and roll it separate from the one that I'm looking at. Then we'll talk. That's what independence is like. But the thing is, we have a definition of independence that we just worked out. It's right here. So we just need to check this equation. If it's true, they're independent. If it's not, they're not. And then we have to reckon with the outcome. And some people worked it out and they said, okay, the probability that both of them occur is 1/3. Their probabilities are 1/2 and 2/3. You multiply that out, you get 1/3. So yeah, they're independent. We have to deal with the fact that they're independent, even though they're looking at the same random variable, this capital X. And I have a homework question about this. I'll just kind of hint at it now. It's not maybe so surprising as it first seems that A and C are independent, because when you have a six-sided die roll, you can think of that, if you want, as a coin flip plus a three-sided die roll. So now you have a coin flip and a separate die roll generating the other source of randomness with three possible outcomes. That's another way to sort of simulate a die roll. And in that context, it's clear that the coin flip and the die roll are separate things, or the three-sided die roll is separate from the coin flip, and yet you have the same probability measure. So sneakily, a die roll is kind of two independent experiments being run together in one go. And from that point of view, you can set it up where C is pertaining to one of the sources of randomness, the coin flip, or actually would have to be the other one, the three-sided die roll, and A is pertaining to the coin flip. So there's something kind of subtle going on here beyond just like checking the definition and, oh, it works out. But in any case, checking the definition is adequate to confirm that these events are independent. So yeah, so just kind of more elaboration on this point. The concept of having nothing to do with one another, you have to be a little careful with that. There are situations where it will lead you astray. Ultimately, independence is a function of the probability measure. So it's not really a function of how the random experiment is set up. You have to know what's the probability measure. Does it give rise to independence or not based on the equation? So if you insist that independence must mean literally having nothing to do with one another, that's not adequate. That's an incomplete view of the story. So we want to bootstrap our way from talking about independence of events to talking about independence of random variables. And the way we do that is we say, so for any two random variables, X and Y, we can ask for the event that random variable falls in a particular subset of the real number line. We can do separate subsets for the two random variables. So let's say X is in A and Y is in B. We can ask that question for any subsets of the real number line. And that's an event. And we want to insist that all of those events are independent. So this is much more ambitious. Instead of one little equation that has to be true, we're insisting that any subset of the real number line you dream up, and then another one separate from that, anytime you form these two events, those are all independent of each other. So this seems like maybe it's too ambitious. Like, how would you possibly satisfy all these conditions at the same time? And it turns out there's a pretty manageable way to do that. And I think I'm just going to maybe skip a few of my messages so that we can get straight to the pictures and have a couple minutes to spend on them. So the idea, if we want to build up a probability space that allows independent random variables to exist, is we just do it with a Cartesian product and we just multiply probability masses. So we use the set of ordered pairs, one element from the first probability space, one element from the second probability space as our probability space. And for the probability mass function, we just multiply. So for every tuple, you multiply the mass coming from the first probability space, times the mass coming from the second probability space, and that's the mass for that particular outcome. So I realize this is not something you can really get a lot from if you're not, inclined to read mathematical notation. There's whatever Greek letters, and there's no pictures here. So I want to put multiple pictures with this to help elaborate. So this is the product space construction. This is how, if you want independent random variables, this is how you build them. And we call P the product measure and omega comma P the product space. So here's a picture, which you might have already seen. I also have some new ones here in a minute. If we have one sort of distribution here depicted along the number line, and another one, and we want to form the product measure, we just go through and multiply all those things. Like this probability mass is really small. So when it multiplies by each of these, we get really small masses here for these particular outcomes. And same for all the other ones. If you have a couple of big ones, they get together to make a pretty big one. But ultimately, all the masses are smaller because there's a lot more things here. There's 25 things to spread the mass out among instead of just 5 along each of the axes here. So, okay, I want to make this concrete because that's the only way it's going to be really clear. And specifically, I want to look back at the example at the beginning of the class. So I showed you a probability measure for the pair of random variables that one of them looks at the number of heads in the first 2 flips, and the other looks at the number of tails in the second 2 flips of 4 fair coin flips. I want to show you how you could come up with that measure just from the 2 marginal distributions and the fact that the random variables are independent. So we have here our quarter, half, quarter probability measures. I got this one spread out along the horizontal axis, this one spread out along the vertical axis. You can see this one's appearing twice because it's a little bit darker. And what I'm going to do is just multiply along these vertical lines and horizontal lines going through these masses. So I haven't seen this done in a particularly great way. I just came up with this one. So you can imagine sort of swinging the masses across the grid here to come up with this product structure. So you can decide whether this really speaks to you. But like these 2 halves, you can see them colliding to give a 4th right there, which I think is pretty fun. And then ultimately, this is what the product measure looks like. So this is a kind of animated version of this picture in a little bit simpler context. We just take all these masses, and we multiply them along horizontal and vertical lines. So when we roll it back the other way, these masses will sort of pile up and give us our original distributions back. When we multiply them out, that gives us our product measure for the 2 separate experiments. Okay, so I think that's a good stopping point. So this bit at the end, it was a little fast. Next time we'll go through it again and break it down a little bit more. I think it's super helpful to really see this stuff done slowly and carefully, though. It's a bit of a luxury we have doing this over the summer instead of during class. And hopefully folks will have a chance to really kind of anchor this in their minds.